Okay, welcome to part 3 of chapter 6. So let's pick up where we left off and let's address the fourth of 5 types of problems for network problems, and we're going to discuss the shortest route problem. And this is something that most of us would be very familiar with, certainly in our contemporary extended use of Google Maps and other GPS-based solutions that we have certainly on our phones now in this era, and it's a wonderful technology. And we generally want to find the shortest route. And some cases you know well probably that you can vary that to find routes without tolls or with no cost or with the least traffic. There are different things variables that can come into play with regard to constraints. Those are all constraints that you would impose upon the shortest route. And of course, you could also incorporate speed variables into that shortest route, not only in terms of that would be a variable measuring time, not just distance. So let's look at what some of the background of some of this. I've asked you in discussion 3 to spend a little time investigating and reading about the work of Edsger Dijkstra, who some 50 plus years ago developed the algorithms that make things like Google Maps possible. So I'll leave those details to your discussion posts. And I also want to point out that there are other things that this work is done for, not just things that Microsoft Research would do, and please feel free to look into that in terms of the shortest path, not just routes, because this is used also for purposes of network routing, in terms of the number of hops that you have to go through to connect between nodes on a network, the internet. And so your system performance will sometimes be affected by how many nodes that you have to connect to get from your browser to a server that's serving up that page that you're viewing on your browser. So that comes into play. Additionally, another application is in circuit design. You might not think of that immediately, but if you ever look at a printed circuit board that's, say, in the motherboard of your computer, or even in the circuit board that's very small boards and the like that are built into your phones and so on, the connection points are desired for the shortest route, and as well in terms of integrated circuits and the way connection points are done. So similar principles are applied there as well. Now, there are a variety of software that we use or available to us, not just for the things that we use as consumers in trying to find the shortest distance from point A to point B, but there are other types of solutions that are used for logistics purposes, organizations that have to drive on for delivery and so on and so forth. And so there are different ways. Sometimes the delivery drivers may have to visit a variety of every node on their network. They can't skip nodes. When in our case, we might want to solve for the shortest route, and we may want to skip nodes. For instance, here's a network representation. If we're starting in an example in our text, I'm using this, is Lewisburg, and we're ending up at Paducah. We're trying to find the shortest route. It might be C through J, it might be A, F through L, so on and so forth. We're not necessarily obligated to stop at every node. We merely want to find the shortest route from node 1 to node 6. Whereas other types of solutions may require us to determine the shortest route between all of these nodes while stopping at all of these nodes. So you have to understand what your objective and purpose is. For our purposes, we're going to look for the shortest route between a source and a destination node without an obligation to connect to all nodes. So let's look at how this might work in a hypothetical practice. So in our text, pages 279 to 282, there's a discussion of the shortest route, and there's an example of a company called Gorman Construction. Now, Gorman Construction is given some data with regard to trying to find the route from their office to a destination, a work site, and other possible paths to go there. And we are given a representation that is similar in concept to this particular network graphic, and we're given distances. And there's a manual means by which to set some of this up. You're not going to have to do that. Instead, we're going to go right to an Excel model where we are given distances between nodes. Node 1 to 2 is 25 miles, node 1 to 3 is 20 miles, and so on. And these are the data distances that are given in the text on page 280. If you were to do this for a test, you might not be given this data. You might have to plug it in. But in a template like this, in terms of having one starting node and multiple intermediate nodes, 4 intermediate nodes, nodes 2, 3, 4, and 5 would be intermediate nodes, and a destination node 6. This template is set up specifically for that. It would have to be modified were you to use it for different purposes. For a test we would do in this class, I would not expect you to have to modify it. But if you're reasonably advanced with using Excel, you could figure out how to modify it. In this particular case, after setting this up for Gorman's example and entering the distances that were given in the text, we merely invoke solver. This is set up for min, not max. Simplex LP, correct. Let's solve here. In this case, our minimum total distance is 32 miles, and these are the routes we would use. We would go from 1 to 3 would be our route. I'm going to color these green. We would go backwards from 3 to 2. We would go from 2 to 4. And we would go from 4 to 6. So we actually touch nodes 1, 2, 3, 4, and 6. We don't touch node 5 in that particular example. And 20 plus 3 is 23, plus 5 is 28, plus 4 is 32. That is the shortest distance for this particular example. And that's how you would look and determine, based on what decision variable comes up with a 1, whether or not you want to take that arc, that path. Okay, pretty straightforward. Pretty simple. Hope you're following along. Okay, let's pick up on the last type of problem, the maximal flow problem. What we really want to do here, we want to identify the maximum volume of flow, whether that's some fluid, water and oil. Think about distribution of those types of things. There are pipelines and distribution networks and irrigation systems and so on that are used in the real world for which these principles apply. It could be flow of people. It could be flow of cars over a highway. It could be flow of electricity over a distribution network of power lines and so on. And we're going to simplify this and call an originating node. We'll identify it as something we're going to call the source, and the destination node we're going to call the sink. And what we're really trying to do is identify the maximum arc flow capacity over all of the arcs in this particular network. Now let's look at one thing that varies in terms of how this is done. In this case, we'll look at maybe the flow of something with regard to planes, say between a source and a sink. And so on, and San Diego being source, Tampa being sink. One difference is that we were seeking to solve for this variable x, the maximum flow from the sink to the source. That's what we're attempting to identify, the maximum flow that goes between the sink and the source. Now, let's look at a particular example in the text, pages 280 through to 286. And this is an example that's given through an interstate highway system in and around the city of Cincinnati. And we're trying to solve for maximum flow. So this is a max problem, not a min problem, right? It's a difference. It's a max problem. The other cases, we were generally solving for min. Now, the text gives us the data on page 284 with regard to the number of nodes. We have 7 nodes, and you'll see in the text of figure 617 on page 284 that there is that connecting arc from the end, from the sink node to the source node, just like I have here with this particular example. So we have that flow, and that's what we're really trying to measure and identify for that's the maximum flow between those 2 points. We're given also the number of vehicles and capacity and so on and so forth. So what does this look like when you set this up in Excel? So I've got an example loaded out there since that a max traffic flow. We've got capacity between nodes. That's given to us in the example in the text. So I merely copied or entered those data there. This is, of course, customized for this particular example. You'd have to modify this example if there were a different configuration. I will not expect you to do that for a test, but in the real world, if you ever wanted to use a model like this and you're sharp with Excel, you could do that. So in this case, we simply invoke solver, go with sanity check. Yes, we're set up for max, simplex LP. Let's run here. And in this case, a maximum flow, whatever our units are, in this particular case, it's vehicles. All right, we're set up, we can get flow of 14. And you can see here, in terms of the outcomes, let me back off from solver again, okay, so that you had, if we did this, all right, I'm going to say call these zeros. Pardon me, let me clear these. All right. Run solver again. You see these zeros are going to change the units, what the optimal solution. I didn't save that, pardon me. Okay. You can see our flow from the sync node back to the source node, 7 to 1 is 14. Exactly what we have here. So these are the number of units shipped, or in this case, the auto is flowing based on the optimal solution. Okay, so generally speaking, I'm only going to ask you for things like the optimal solution. In this case, the answer will be 14, whatever the appropriate units are. In this case, they are given as vehicles. Okay, so we've gone through all 5 particular types of problems. I'm going to put some problems out on Canvas, some additional practice problems, number 2, number 3, number 4. Pardon me, number 2 and number 3. I apologize. Only 2 and 3. You do not have to be concerned with doing parts A and B on either of these, and I will put these out there. You can look at the answers on the examples of templates I'll give you to decide the optimal distribution plan, the total cost, and so on. I want you to get used to doing this. And here's a little breakdown of what we're going to see on the next test with regard to Chapter 6. It's going to open early afternoon on July 10th. Close on the 15th of July, so you're going to get 5+ days. Midnight on the 15th of July, there are going to be 11 questions. 7 of them are going to be definitional, true, false, or multiple choice. 4 are going to be problem solving with Excel with Solver. I'll provide the templates. We are definitely going to have transportation assignment and transshipment problems. I may add a shortest route problem to that as well. We'll see, but I've given you an example and a template example for each of these. I think you can probably handle it. All right, that concludes week 6. That concludes chapter 6. I thank you for your time and attention, and please feel free to reach out to me if you have any additional questions. Thanks very much. I'll see you next week. Bye-bye.